Okay, good morning to all of you. Now, my students, you have already seen my previous lectures on gamma ray spectroscopy, and in this one I am going to talk about some of the aspects which I have not covered till now. So let's first start. What we are going to concentrate on is this transition from your master degree lab and MSc lab to research level. That means PhD plus postdoc and whatnot. Now on this side of the screen here you can see this is a typical gamma spectrum experiment using sodium iodide scintillation detector, which is this one, and you are seeing the spectrum after preamplifier, amplifier, discriminator in the laptop. Here this is a very simple setup, and you do this in MSc Advanced Lab as a part of your MSc curriculum. And on the right side here, this is what I am talking about, the research level. This is one of the gamma sphere very important arrays, state-of-the-art arrays, gamma sphere array. And what we are observing is just gamma spectrum. Of course, so many detectors, things will be much more interesting over here. So let's proceed with this. Okay, so now you see what we want to do is basically a qualitative study of the energy spectra from a decaying nucleus. So a nucleus is decaying and it emits gamma rays everywhere. Now what I am doing is I am going to put a detector nearby and then plus electronics, associated electronics. Now I have talked about this electronics part in separate video, so I am not going to talk about it. So when the gamma ray enters this detector, it interacts with it, right? And as a result of this interaction, what we will see is a spectrum. And what is the spectrum? The x-axis is basically energy, so we are observing energy spectrum, right? So this is energy in keV, and here is just counts. Okay, and you can see many things as a result. We will talk about it. What should we observe? So you must be wondering, what do we observe and why do we observe? Right, so I'll be talking about this part briefly soon. Okay, so that's the idea. Good. So what next? Well, you see, as I was saying, we just have to analyze the spectrum. And again, as I was asking you, what do we gain by analyzing the spectrum? Of course, we are talking about gamma ray, right? And gamma rays are emitted as a result of the nuclear de-excitation process. So since it is the nucleus which is de-exciting them, which is emitting them basically, so gamma rays tell us information about the nuclei, or more importantly, excited nuclei, right? Now, you see, we do know that our nucleus is a many-body quantum mechanical system. Why? It consists of so many nucleons, protons and neutrons, and they are quanta, right? They are quantum mechanical particles, fermions. Also, the nucleon motion inside this nucleus is described mainly by a mean field. And what is the mean field? The mean field basically means that if there are a large number of nucleons inside the nucleus, so the mean field concept is that, let us consider this particular nucleon. Now you must be wondering what is the effect of the other nucleons, this one, this one, this one, on this, right? You must be wondering. Now in the case of mean field, what we do is we consider all the effects of the interactions of all the other nucleons and sum it up as an average potential. So overall the result is that the particle is basically moving in a single body, a simple quantum mechanical potential is just like that, an average potential. So this is the overall beauty of this mean field. So basically I am converting a many body problem to a particle in a potential well. Very simple. Now this we have done starting from our graduation. So you see, we are back to again our graduation class. Anyway, so this is the overall idea. Now also you see the excited states, they're strongly dependent on the nature of the mean field, and this is what makes things very interesting. So mean field basically decides what the excited state, its behavior would be. And so it is very important to have knowledge about the excited states, and then only we will be able to understand the nature of the mean field. Okay, so what we are going to do is we are basically going to study the structure of the atomic nucleus using gamma ray spectroscopy. And so for that, as I was saying, what was I saying? Well, I was saying that the gamma rays were emitted as a result of the nuclear de-excitations, right? So first I have to excite the nucleus, and how I am going to do that? Well, by means of a nuclear reaction or by the decay of another nucleus, right? And then I am going to observe those gamma rays by putting a appropriate detector nearby and then observing the signal. So this is what our game plan is, right? And what do we gain from that? You must be wondering. Well, you see, how many nuclei are there? Have you thought about it? Well, of course you do know, right? Approximately 6,000 or more nuclei are predicted to exist. And this is very interesting if you do a plot for that. And the plot is proton number versus neutron number, n by z, the celebrated chart of nuclides. And here what you see is a very interesting structure. You see a valley, and here lies in the center of the valley over here are the stable nuclei, more or less. And as you move away from this stability region towards the outer part, what happens? The lifetimes, the mean lifetimes, they decrease. That means nuclei become more and more short-lived, more and more radioactive. Okay, so as I was saying, only 3,000 nuclei are known roughly till date. And so there is so much scope for you newcomers to do experiments and theory and try to find the other half of the story, right? And our basic strategy will be like this. Suppose you want to understand the nature of a person. What you do? You know about the interviews, right? In the interviews, there is a psychological part as well. They test you by asking various type of questions. In one question, they will try to anger you. In another question, they will try to demotivate you. Through another question, they will try to mock you or something. And the result is that they will observe your behavior. That means how you respond to those questions, and through those questions, they will try to analyze your nature, or basically whether you are fit for the job or not. Now similarly, for our atomic nucleus, what we are going to do is we are going to excite it. Now when I am saying excitation, you think of the atomic nucleus as if it can have any value of n by z. It can have, if I excite it to a very high angular momentum, that is also possible, right? Or it can have a large value of isospin. So basically I am going to study, we are going to study the atomic nuclei along 3 dimensions. One is large n by z over here, next is large angular momentum, high spin study, and then high isospin, this one. So interesting. So these are basically the extreme conditions. So we are going to put the nucleus to extreme conditions and study it, and from there we will be able to understand more about its nature. That's the overall idea about how experimental research is done, mainly regarding the gamma ray spectroscopy I am talking about. Okay, good, fine. So now you must be wondering, okay, so this is yet another basic science approach where we study without giving anything to our society, right? Yet another philosophical aspect. No, absolutely not. Well, nuclear physics has a lot of applications. Well, and talking about applications, I'm talking about saving lives, right? Human lives. Now just to give you an example, look over here. You see, using gamma rays, we can use these gamma rays basically to kill the bacteria living on fruits such as strawberries. And what will happen as a result? Well, they will last longer, right? But you must be wondering if the gamma irradiation affects the quality of the fruit. No, we will keep it quite, the dose will be very small and the gamma rays will be chosen appropriate so that it doesn't affect the quality of the fruit. You see, many meats such as chicken, pork are also irradiated. So you can say, if you save the food for a little while longer, a lot of more and more people will be able to eat it. So in a way, you are solving a sort of hunger problem. Well, this is just one aspect of it. Another aspect, you can see this Mangalyaan, our satellite, great Indian pride. Well, so there are a lot of gamma ray detectors on it. And why do we need that? Well, we want to understand if there is some nuclear activity going on Mars or nearby places. And that will tell us many important features about what was previously over there. Right. Well, this was application number 2. Application number 3, you must have heard, nuclear medicine. So, suppose there is something wrong inside someone's body. One way to understand it is to cut it open, and that will be quite painful. So must be wondering, well, is there another technique which is not that painful? Well, of course there are. Another technique is you put a light bulb inside the place where there is having some problem inside the body. And so when the light glows, you will be able to see clearly what is going on inside the body. And how do we do that? Well, put an appropriate radioactive nuclei. I am saying appropriate, which has very less half-lives, say 6 hours, 3 hours or so, in a liquid form, along with a particular agent which will, after engulfed or through injection, it will take the radioactive nuclei to, yes, so as I was saying, so if engulfed, it will take the radioactive dose to the proper place where there is having some issue, and then gamma rays will be emitted from the radioactivity, and that place will be illuminated. And if you put gamma detectors outside the body, you will be able to observe those gamma rays. And when they penetrate those places, and as a result, through the absorption of gamma rays, you will be able to get some features, idea about that particular place as well. That's the idea, and this is basically the nuclear medicine part application. Well, of course, you are hearing about all the nuclear bomb, atom bomb. They are all a result of applications of nuclear physics, but not for the goodness of mankind. Anyway, that's yet another application. Okay, so what more? Finally, okay, so here we go to our MSc lab, and what you see here is the following. Well, we have our famous GM counter, right? So the first is the GM counter, and what do we do? Basically, total counts of the entire spectrum. Here we observe it. Okay, now this is one of the most basic experiments in the MSc lab. The second one, a little bit more advanced, is the single channel analyzer. So here we observe counts corresponding to an energy bin, and after full scan of the energy region, the total spectrum is observed. So it's like this, energy bins, we observe the spectrum and we basically scan the spectrum in this single channel analyzer experiment. Normally we use sodium iodide detector with it. Well, I have made several videos on this, you can check it. Well, and finally is the multi-channel analyzer, and here what's the difference with the single channel is that here we observe the entire spectrum all at a time together. In the case of single channel, you have to say that preset time is 30 seconds, then you have to take the reading over here for 30 seconds, next 30 seconds, next 30 seconds, and this way you sweep the spectrum, right? But in the case of NCA, you don't wait for 30 seconds or something like that. You turn on the knob after the source is there with appropriate setting, and you will start seeing the spectrum. And interestingly, after some time, say 1 minute or so, you will see the spectrum keeps on increasing and keeps on increasing, right? So everything is coming together over here in the NCA. Fine. Okay. So now, yes, so as I was saying, as a gamma ray spectroscopist, we are looking into this path from MSc lab to research lab to advanced research lab in various accelerator facilities and so on. Right. Okay. Now, so the next very trivial question, just to tell you, well, of course, what is gamma ray? As I was saying, nuclear de-excitation process, they are emitted, right? And here is the entire electromagnetic spectrum. You can see the place of the gamma ray in it is very high energy, and the frequency you can see is very high. Okay, now, so again, origin of gamma rays, as I have told you, as a result of nuclear de-excitation. Suppose some nucleus is excited to a higher level. Suppose these are the levels of a nucleus. Suppose this is excited to this part, and then there is a possibility of gamma transition or also its competitor internal conversion. But again, this will be true if there is no other competitor like proton emission, neutron emission or alpha emission. So I am talking about very low energy, lower than 8 MeV or so. Right. Now of course, if the nucleus gets excited to this next higher level, there can also be a possibility. Now this gamma ray, this is a possibility that it can go to this subsequent level or it can go directly to the ground level. So this you have to check through the level scheme. These are the possibilities. Okay. Fine. Well, I need not tell you, you must know this, that all the nuclear levels, they are leveled by appropriate and unique spins and parity quantum numbers, and they have, of course, different energies. That's why I am placing them like this. Okay? Fine. Now, here are more examples of the excited spectrum for the other nuclei, starting from 25 aluminium to 120 tellurium. Okay, you see, each nuclei has its different energy level. Okay, so what's the philosophy? The philosophy is to detect gamma rays, and for that we have to let the gamma rays interact with matter, and then not just interact, it must lose energy in the detector. Remember the first plot I was saying? The gamma ray must lose energy in the detector. So it's the detector, the gamma ray comes, and if it just goes away, hello, no interaction, that won't do. Wrong. We don't want that. We want the gamma ray to interact. That means it must lose some of its energy over here. Now I must tell you more about how it loses energy in the medium. The primary methods, the primary reasons for losing its energy. Well, there are three processes due to which it loses its energy. Mainly, one is photoelectric effect, single shot. Another is Compton scattering. Remember the scattering process, collision process of a photon and electron, the Compton scattering. And the third is pair production. Now you see, okay, so now here you see, so full energy deposition, when will it be? Suppose 1 MeV gamma ray comes, I want all of the 1 MeV to be deposited in the detector, right? And so the question is, how is it going to happen? Well, one possibility, if the gamma ray undergoes photoelectric effect inside the detector, so entire energy is absorbed as a result of the absorbing of the electrons, right? The Kx rays and electrons and all that, they are all absorbed inside the detector. And the second possibility is Compton scattering happens. Okay, say for example over here, suppose Compton scattering happens, but after that there is a photoelectric effect. Or again, suppose pair production happens, then electron, positron are emitted, electron is absorbed, then the positron after some time it interacts with electron and then 511 kV are emitted, but all of these are absorbed inside the detector. That means all the 511 kVs are again, they are finally absorbed by photoelectric effect along with the other electron and positron. And if this happens, then what we will have is we will have the full energy deposition. But if the process is not followed by the photoelectric effect, then some part of the energy is likely to be lost. How? Because there will be some small scattered gamma ray which will exit the detector, and as a result we will deposit lower energy or partial energy. Right, let me again show this to you. So the idea is the following: I want gamma ray to be completely absorbed. This is shown over here. The next possibility is it comes over here, undergoes Compton scattering, then again it undergoes Compton scattering. So Compton scattering 1, Compton scattering 2, and you see again Compton scattering. But this third one, this gamma ray, it goes outside of the detector. So how much energy will be deposited? So suppose if this is 1 MeV and this is say 700 kV was deposited over here at this point, and then this gamma ray was 300 kV. So you will see, suppose this gamma ray is of 20 kV, let me say, then the overall energy which will be deposited is what? 1000 kV minus 20 kV. That means it is 980 kV, and this is not what we want. So this will contribute to the background, and particularly in this case multiple Compton background, right? This is one example I have shown you over here. Okay, now let's see the spectrum from a monoenergetic gamma ray source, right? What do you see? Well, suppose n gamma rays of energy E0 enter the active volume of a detector, right? Over here, as you can see. So n gamma rays, right? N gamma rays, right? And they have energy E0, no problem. Active volume. Now, if the detector is very large, what will happen is that some gamma rays escape without any interaction, and this can happen for smaller detectors. But here, what will happen is all of them will interact with the detector, and all the particular effects after that, Compton scattering, pair production, all these things, they will happen inside the detector, right? And so you can see that there is a more or less gamma interaction volume like this, where all the processes, Compton scattering, pair production, blah 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 blah, multiple Compton scattering and all that, they will be absorbed, and as a result we will observe only full energy peak. And this is what you can see over here. Look, only full energy peak, no background. Well, life is so cool. Had it been so. Unfortunately for all of us, this is not possible. Why? Making such very big detectors, number one, is nearly impossible from manufacturing standards, right? Manufacturing process is very impossible, very hard. Number two, very, very costly. Number three, very important, Doppler broadening. You see, if I have a source over here and this is a detector, then the detector is seeing this angle in the source. That means all the gamma rays which are emitted within this angle will be detected by the detector, right? This is the idea. Now, if the source is fixed, I mean the source is at rest, then no problem, everything is fine. But suppose in a nuclear reaction, target, this is the projectile, reaction happens, and as a result the product nuclei is also moving, and if it emits a gamma ray, and those gamma rays emitted by the moving nuclei, if they are detected by a detector, then this theta angle will be very important. Why? Because of Doppler broadening. If this detector opening angle is very large, then you will see a very broadened peak, and if the gamma ray was at rest, you will see something like this. But if the if the source is at rest, you will see something like this. But if the source is moving, you will see like this. Why? Because of the detector opening angle. So we need detectors with very small opening angles. We cannot have very large detectors. Okay, this is from physics viewpoint, the restriction. 3 restrictions I mentioned. Okay, so we use a very standard detector, right? And what happens in the case of a standard detector? Again, n gamma rays enter, but here you see this time the interaction volume is actually bigger than the detector itself. So this means there is a possibility that some of the gamma rays, multiple Compton scattering, or the 511 keV or 511 keV, again Compton scatters, they will be leaving the detector, right? There is a possibility, and so there will be some gamma rays which will escape, right? There is a possibility, and as a result we observe this. So previously we were observing only the full energy peak, but now there will be a lot of stuff in this region, and this is all due to partial energy deposition. And remember, this is unwanted, we didn't want it, but there is nothing we can do. This is the way it is, and this is all background, part of the background. Okay, any questions? Okay, so if there are none, let me proceed. Okay, so here I am showing you a simple detector. This is, you see, the green one is the HPG crystal, and the surrounding material is shown outside in the yellow color. Now let us consider the various possibilities. So basically what I am talking about is introduction to gamma spectrum. How you see. So basically how you see what you see. Okay, I'm trying to answer that. So let's see over here. So basically the first case is when 1 MeV is absorbed. Now complete photoelectric effect absorption, no problem. So as a result you will see at 1 MeV in the axis count 1, you see 1 count. So this corresponds to complete absorption. In the second case, case 2, suppose 700 kV is absorbed and 300 kV gamma ray is scattered outside. What will happen? Now you see how much is absorbed, 700 kV. So at 700 kV over here, you see we will observe a count, single count, 1 count, and this is due to case 2. Next, case 3, 700 kV is absorbed. Here the gamma ray doesn't enter the detector but outside and scatters, and as a result of the interaction, Compton scattered gamma ray of 300 kV, it exits this outside material and this enters our own detector and is absorbed. So how much will you observe? We will observe just what is absorbed by the detector. We don't know what is outside. Whatever the detector absorbs, we will observe. So we observe the 300 kV gamma ray. Okay, well, it's not shown over here, it will be like this over this place. So 1 MeV, the first case, let me write it separately. So let me write it separately, right? This is 1 MeV, this is 500 kV, this is 4, 3, 2, 4. So this is say 100, this is 200, this is 300, this is 400. Pardon me, I mean my scaling is not quite correct. Anyway, let me give you the idea. For that idea, this is okay, right? So the first case, I am seeing a count over here. This is case 1, right? For the second case, how much is absorbed? 700 kV, 5, 6, 7. So if this is 700 kV, I will observe a count over here. So this is case 2. Okay. Next one, case 3. How much is observed? Only 300. So at 300, I will see a count over here. This is case 3. And next, finally, case 4. What is happening is that first the gamma ray interacts inside the detector and 700 kV is absorbed. Good. And 300 kV gamma ray scattered outside over here, where 200 kV is absorbed and 100 kV scattered to the detector again, where it is finally absorbed. So how much is absorbed total? Total is 700 plus 100, 800, right? So at 800 kV over here, we will observe a count, and this is our case 4. So you see, I have shown you 4 possibilities over here, and what you will see in the spectrum as a result of this. Fine. So here, yeah, unfortunately it's not shown here, so I am showing it over here. So this is how it should be. So Any questions again? Okay, yeah, so I think that will be satisfactory to you. Fine. Okay. Now, before I proceed, let me just show you this plot yet again. So as I was saying, you see, when gamma rays enter the detector, not all of them will interact. Of course, some will be just escaping without interaction. Right. You see, what I have done is, n gamma rays enter the detector. So basically, I am saying is, n gamma rays enter detector. Next, out of these n gamma rays, you see, some will interact with the detector, and some will escape without any interaction. Let us call them NE. So escape without interaction. Now out of those which will interact, again there will be two parts. One is, some will deposit full energy, and the next will be, of course, the other ones which will deposit partial energy, not full energy. So they are not fully absorbed, and these ones are fully absorbed. So this is total N, this is NE, this number, and the numbers that will interact, how much it will be? It will be basically N minus NE, right? Now the sum which will deposit partial energy, that means which are not completely absorbed, let me call it Ni, right? So what is this number which will deposit full energy? It will be N minus Ne minus Ni. See over here, this is what I am saying. And if you try to ask me, sir, what is the overall efficiency of this mechanism, just like in thermodynamics, here instead of efficiency we are talking about full energy peak efficiency. That means everything over here, you see. So everything we want is over here, but unfortunately this will be there, the background. But again, so what is the full energy peak efficiency? Of course, the full energy peak efficiency is total counts which are absorbed, that means this number over here, divided by the total gamma rays which have entered the detector, N. So this is the full energy peak efficiency, N minus Ne minus Ni. That means those which are fully absorbed divided by the total gamma rays which enter the detector, right? I think I have explained this to you. Okay, so now let me move. So here what I am showing you is the following. You see, for a detector, if we increase the incident gamma ray energy, what will happen is that this interaction region will keep on increasing. Why? Because more and more processes can happen, and the scattered gamma ray, they will be higher, and as a result there will be more possibility of exiting the detector. So you see, in this case E1 is smaller. That means the incident gamma ray energy, if it is small, then the overall interaction will be contained in this volume. If the E1 is higher, say E2, then the overall is contained over here. Still now there is no problem, full energy is absorbed. But from this case over here, E3, you see, so what I am showing you from the figure, we will observe only full energy peak for E1 and E2. But for E3, we will observe Compton scattering. Okay. Now this plot is not correct. Why? Because the energies are different. So say this is around lower energy, this is low energy, and this is higher energy, right? So we will observe also as a result of this, and if this will be added to this spectrum, and also there will be effects due to single escape peak and double escape peak. Escape peak effects will also be there if the 511 keVs exit. Anyway, And why I am talking about this? Basically, what I want to address, just now I have talked about the full energy peak efficiency, right? Now I want to know whether this efficiency increases or decreases with energy, and the result is, you can see. And what's the result? The result is like this. The efficiency basically decreases with energy. So if this is gamma ray energy and this is the efficiency, it keeps on decreasing. Why? Because at high energies, gamma rays interact less. More will be getting away from the detector without interaction, and whatever we will be detecting, the photoelectric effect, the cross section becomes smaller at high energy. So as a result of which, the complete absorption will be much smaller, and instead Compton scattering and pair production interactions are larger, and so background will be more comparatively. Okay, and lastly, let me show you this plot. Here what you will see is the following. First, this one, what I am showing you, just now I have shown you this plot, right, which is the efficiency as a function of gamma ray energy, right? This is overall decreasing trend is there. Now what about the volume? Here you see this plot. Look, here I am talking about again full energy peak efficiency, but I have taken a cylindrical coaxial geometry, and here I am shown the efficiency as a function of this d. What is this? D. This is the diameter. So if I increase the d, or means the volume, you see the efficiency increases. And why does it the efficiency increases? Well, of course, the answer is over here. If the detector is very large, what happens? Slowly, if I increase the d, this basically I am increasing the detector size. So all the interaction will be contained inside the volume, right? And this is what is happening because I have fixed the energy. So basic idea is I am fixing the gamma ray energy and slowly increasing the detector size. Of course, what will happen? Keeping the length fixed. So of course, the gamma interaction volume, which was supposed previously was here, it will be now contained within this, and as a result, the peak efficiency will keep on increasing, right? So this is the explanation. And on this side of this plot, you can see the full energy peak. The peak to total. And what is that? Remember, this is what we normally observe before pair production threshold. So I am not talking about the escape peaks anymore. Now this is the full energy peak. Now there is yet another, along with efficiency, there is another measure, and that is your peak to total. That means the total full energy peak counts divided by the total counts. That means everything that is in the spectrum, total counts, that is the T. And this, you see, this also keeps on increasing with the diameter. Why? Because if I keep on increasing the diameter, the same thing will happen. The detector interaction region, the volume will be less, will be contained inside this larger detector. Now as a result, more and more peak counts will be absorbed. And what will happen is that, let me show you interestingly. So suppose I have got a smaller detector, right? Smaller detector, and from there we are seeing something like this. Let me say, now if I increase the detector size, what will happen is that this part will get much reduced and the full energy peak will increase. And what is happening? Basically, if you compare, if there are equal number of gamma rays interacting with both of them, if I do this, then what has happened is that you see, subtraction, the background is subtracted. So what is happening? Basically, whatever background was there in this case, they have gone back to the full energy peak. And this is the result of the increasing of the peak to total ratio with increasing volume. Okay, good.